there have been many changes in the environment of the Earth through time, but there's probably little doubt in saying that one of the most important changes was the rise in oxygen in the Earth's atmosphere, the oxidation of the atmosphere. And why is this important? Well, oxygen makes possible aerobic respiration. Oxygen can be used to essentially burn organic carbon in a controlled way, of course, in organisms and release great quantities of energy, which can probably allow for the complexities of multicellular organisms. So the rise in oxygen in the Earth's atmosphere had profound implications, as we'll see, for life on our planet. We know from the rock record, and we'll see how this is the case in a while, that the oxygen on the early Earth, the very early Earth, at least 4 billion years ago, was much lower than it is today, much less than 0.1% of present atmospheric levels. And this raises several questions of interest to astrobiologists. When did oxygen become abundant? What was the cause of this rise? How do we track the rise of oxygen in the atmosphere? How do we figure out what level of oxygen was in the early Earth atmosphere? And how did this change affect life on Earth? What were the consequences for the biosphere? Well, this graph just shows you how oxygen has changed over time, and we can use things called proxies. These are geochemical indicators in the rock record that tell us something about the concentrations of oxygen. Minerals, for example, and rocks that behave in particular ways when they're subjected to certain atmospheric concentrations of oxygen. And the way in which those minerals behave can tell us what the levels of oxygen might have been in the atmosphere. And we'll come back to that in a moment. But it's important to recognize three essential major periods of oxygen throughout Earth history. First of all, a very early period from the formation of the Earth through to about 2.4 billion years ago, when oxygen levels were very low, much less than 0.1% of oxygen in the Earth's atmosphere. And then about 2.45 billion years ago, a sudden and abrupt, at least on geological timescales, rise in atmospheric oxygen to about 10% of the present atmospheric level. And then roughly about 500 million years ago, 600 million years ago, another rise in atmospheric oxygen up to present-day levels, around 20% of the Earth's atmosphere, although it's varied over the last few hundred million years. But the question we want to address here is, what caused this first abrupt rise in oxygen? What would cause oxygen in a planetary atmosphere to rise very abruptly? Well, first of all, we might question, how is oxygen produced? Where does it come from to rise in the atmosphere in the first place? Well, the main source of oxygen in the atmosphere is photosynthesis. That's the main biological source of this gas. Photosynthetic microorganisms such as cyanobacteria produce oxygen in photosynthesis as a waste product of oxygen, and that can build up in the atmosphere and give rise to high concentrations of oxygen in the atmospheric composition. But oxygen is also taken out of the atmosphere. There's a balance between oxygen being produced and oxygen being removed. How can oxygen be removed from an atmosphere? Well, two mechanisms by which this can occur. Firstly, oxygen binding with dead organic material, dead organisms in other words, and reacting with that organic material and being removed from the atmosphere. So when an organism dies, it's essentially a lump of organic carbon, and that organic carbon can react, can oxidize with the presence of oxygen in the Earth's atmosphere and consume atmospheric oxygen in the Earth's atmosphere. And you'll understand, of course, that means that if we bury a dead organism before it gets a chance to react with oxygen in the atmosphere, we can actually get a net production of oxygen in the atmosphere. We can actually increase the oxygen in the atmosphere by burying organisms in sediments or in sands before that organic material can have a chance to react with the oxygen and remove it from the atmosphere. Another way in which oxygen can be removed from the atmosphere is by reacting with reducing compounds, things like hydrogen sulfide or hydrogen, compounds that will tend to react with oxygen in chemical reactions and thereby remove it from the atmosphere. And a source of these reducing compounds is volcanic eruptions. There's just one type of environment that can produce gases that can react with oxygen and remove it from the atmosphere. So these are the ways in which oxygen can be removed from the atmosphere, and we saw how oxygen can be produced by photosynthesis. So if we want to build up oxygen in the Earth's atmosphere, we have to do one of two things. Either we have to take less of it out of the atmosphere so that there is a net build-up of oxygen in the Earth's atmosphere, or we have to produce more by photosynthesis. We think that photosynthesis evolved a long time before the rise in oxygen in the Earth's atmosphere. And as a result, it doesn't seem like that's a good reason for the rise in oxygen in the Earth's atmosphere, that photosynthesis suddenly became more active and produced more oxygen. One possibility is a sudden reduction in the gases being produced by volcanism that would mean less oxygen was being removed from the atmosphere. Another possibility is that there was an increase in the burial of dead organisms. If we increase the burial of dead organisms, bury more of them more quickly, they'll have less of a chance to react with the oxygen in the Earth's atmosphere, and so oxygen will tend to stick around in the atmosphere and not be removed from the atmosphere in those dead organisms. We also may have had a switch between two stable states. Maybe the atmospheric dynamics of the Earth was such that all of these factors came into play. At some particular point in the Earth's history, about 2.45 billion years ago, the rise in oxygen in the Earth's atmosphere could have been a combination of things. Increased burial of organisms that prevented them from mopping up oxygen, perhaps a reduction in the amount of gases being produced from volcanism and other sources that could have mopped up oxygen. Maybe some of these, not others, maybe a combination of these events. It remains one of the great enigmas of astrobiology to try and fathom out why oxygen rose so quickly. It's undoubtedly also the case, there may have been feedback processes going on the Earth at that time, that once oxygen began to rise, there could have been mechanisms by which that process of increasing oxygen could have been exacerbated and ultimately led to a sudden switch from one state to another. However it occurred, it would have had profound consequences for the environment of the Earth. As the atmosphere became more oxidizing, many gases that are important in climate would have been at lower concentrations. For example, methane, one of the gases that is involved in global warming, in greenhouse warming, in the present day, but also in the past. The rise of oxygen would have meant that oxygen would have reacted with methane, and there would have been less methane in the early Earth atmosphere during that switch into an oxidized state. And that could have had profound implications for the extent to which the surface of the Earth was warmed by methane. As the surface of the Earth switched from an anaerobic environment, essentially an oxygen-free environment, to a more oxic environment where there was oxygen, that would have changed the oxidation states of elements like iron and other sorts of elements important in the biosphere, and that would have caused radical shifts in the geochemical cycling of elements through the Earth's crust with knock-on effects on the biosphere. So changes from an oxygen-free environment to an oxygen-containing environment would have had profound implications for how elements behaved in the Earth's crust. For life, it was a double-edged sword. On the one hand, the rise of oxygen would have meant that those organisms that were used to living on a planet with very low levels of oxygen would have been forced into particular environments where there was still essentially oxygen-free conditions. For example, in the deep oceans, perhaps underground, where conditions were still essentially oxygen-free. It would have been a very bad time from the point of view of anaerobic organisms, organisms that prefer oxygen-free environments, to have found habitats. But on the other hand, the rise of oxygen, as I've already said, would have allowed for aerobic respiration. Aerobic respiration is between about 15-20 times more efficient than many anaerobic metabolisms, many anaerobic ways of making energy. And that rise in oxygen would have allowed for aerobic respiration and possibly the rise of multicellular organisms, eventually giving rise to intelligence. So the rise in oxygen may have been beneficial, perhaps even essential, ultimately for the rise of intelligence on our planet. So we can think of the rise in oxygen as a double-edged sword. How do we reconstruct these past oxygen environments on the early Earth? How do we know that oxygen rose in this way? Well, there are a number of ways in which scientists can do this. One way is to look at the phylogenetic tree, to look at the relationship of organisms and to try and see when the first oxygen-requiring organisms appeared in the tree of life and how that matches up with the geological record. So the phylogenetic tree that we've already looked at in this course is a source of information about the development of organisms, particularly microorganisms on our planet, that can tell us something about how environments might have changed through time and how that transition from organisms that were predominantly living in oxygen-free environments to organisms that needed oxygen would have occurred and when that transition would have occurred. We can also learn something about past oxygen environments from minerals, proxies as we call them, that tell us something about the oxygen environments in which they were formed. Here are some minerals that tend to be formed in environments with particular oxygen concentrations. For example, pyrite, which is iron sulfide, tends to be formed at oxygen concentrations less than 0.1% of the present atmospheric level, 21%. Uraninite, which is a uranium oxide, which tends to be formed at oxygen concentrations much less than 0.01% of present atmospheric levels. And siderite, which is iron carbonate, which is really only formed at oxygen concentrations much less than 0.001%. So if we find these minerals in the rock record, it tells us that they've been in environments where the oxygen concentrations are very low. And if we find very large concentrations of these minerals in the rock record at particular times, it would suggest that the large-scale environment was also very low in oxygen. So these are examples of mineral proxies, geochemical proxies, that we can look for in the rock record and that tell scientists about the oxygen concentrations that would have prevailed, at least in the environments in which those minerals were being formed, but possibly also on the global scale as well. We can also look at elements that are very sensitive to changes in oxygen, particularly in the way in which they dissolve in water. For example, take iron, a very common element. When iron is in a reduced state, Fe2+, reduced iron, it's very soluble in water, but it tends to be in that state much more readily when there's very little oxygen around. When there's lots of oxygen around, that iron will oxidize and essentially form rust, the rust that you and I are familiar with. And rust is not very soluble. If you scrape rust off a rusted metal gate and you try and mix it with water, it won't really dissolve. It'll just float around in the water as a solid. It's not very soluble. But reduced iron, formed when there's very low concentrations of oxygen, is very soluble. And if we look at the changes in these elements throughout history, we can learn something about whether there was high or low oxygen in the atmosphere through time. A good example of this is banded iron formations. And these are layers of iron-rich compounds that were laid down in the rock record before 2.4 billion years ago. Where did these banded iron formations come from? Well, what we think happened is that before 2.4 billion years ago, there was very little oxygen in the Earth's atmosphere. And as a result, a lot of the iron in the oceans was dissolved. It was solubilized. It was mixed with the water in the form of reduced iron, a very soluble form of iron. And every now and again, there may have been some oxidation event. For example, oxygenic photosynthesizers might have produced localized oxygen that oxidized that iron and turned it into rust. It's possible that other types of microbes that like to eat iron as a source of energy and produce oxidized iron, rust, as a waste product of that feeding, could also have oxidized that iron. When that iron became oxidized, it became insoluble. It no longer dissolved in the oceans, and it settled down into the bottom of the oceans and formed these rich iron sediments. And these banded iron formations, these bands of iron, suggest that the iron in the ocean, which was generally dissolved, solubilized in the water, every now and again became oxidized to rust and settled out and formed these great thick layers of red iron oxides. The disappearance of these iron formations, these banded iron formations at about 2.4 billion years ago, suggest that the atmosphere had become completely oxidized. There was no longer large quantities of dissolved iron in the oceans that every now and again would become oxidized and fall out of the oceans. Now the iron was constantly oxidized and so no longer produced these rich layers of iron-containing rocks that were formed when there was very little oxygen in the atmosphere. This is just an example of how we can look in the rock record and by studying elements that change the way in which they can be soluble in water depending upon the levels of oxygen, the way in which these changes occur can tell us something about past oxygen levels in the atmosphere. And that's how astrobiologists learn about how oxygen has changed throughout the history of life on Earth. So what have we learned in this lecture? Well, hopefully we've learned that at about 2.4 billion years ago, there was a sudden switch from a planet in which there were very low levels of oxygen to a planet in which there were much higher levels of oxygen. And probably this switch had profound implications for life. We've learned that the cause of this sudden increase in oxygen is still enigmatic and quite ambiguous, but there are ideas about how that could have occurred and how that rapid switch might have happened. But it remains a continuing challenge in astrobiology to truly understand what the environmental changes were that occurred, or even the biological changes that contributed towards that rapid switch. The rise of oxygen would have probably had implications for global climate by changing the concentration of greenhouse gases like methane, and it also would have had consequences for the cycling of elements vital for life through the biosphere. The increase in oxygen would have had profound implications for life. It would have restricted the habitats available for anaerobic organisms that need oxygen-free environments or very low oxygen-containing environments. But it also may have led to the rise of multicellular life and ultimately may have been necessary for the rise of intelligence. And finally, we've learned something about the way in which we can look at minerals in the rock record to get an idea about how those oxygen levels changed throughout the history of our planet.